I noticed that here there is no tradition to thank organizers, but I thank them anyway for organizing fantastic program. Thank you again. So today I will talk about conformal anomalies and the chiral anomalies in the presence of boundaries. So my first part will be on conformal anomalies. I don't really have anything new to say here, but I will give some sort of introduction into the boundaries and present some short review. And then I will concentrate on fermions and chiral anomaly. And at the end, I will, if there is time, I will discuss possible manifestations of chiral anomalies. And believe it or not, they manifest as electric currents in the presence of external magnetic fields. Okay, so we all know what is the conformal anomaly, but let me remind you. So we have a theory which is a invariant under rescaling, local rescaling of metric. If such a theory exists, classically stress-energy tensor is traceless. And when we quantize this theory, it may be let race may be non-vanishing, and that is the conformal anomaly. So how we compute it, at least in one loop, we consider partition function. Suppose phi is my quantum field, and then T mu is just, yeah, this can be rewritten as some effective quantum action, which is functional of only metric, and then quantum T mu, expectation value, just variation of this quantum action with respect to metric. And if it is non-traceless, it will give us a certain anomaly, which is a local anomaly. It depends on the point in the space-time. And anomaly has, well, in dimension D, it has dimension D. And it can be constructed from any local curvature invariants, or if there is coupling to external electromagnetic field or gauge field, it will also can be constructed from invariant object constructed from a gauge field. All these objects are even dimensional, have dimension 2. And that means that if D is even, there is such anomaly. If D is odd, this anomaly doesn't exist. And that's why in odd dimensions we say that formal anomaly is absent. But the situation is different if my manifold has a boundary. Usually it's space-time manifold, but can be a Euclidean manifold also. The situation may be different because anomaly in that case it is more appropriate to consider some integrated anomaly. Okay, it's T is a trace of T mu, and then it has two contributions. It has a bulk contribution, which I will write as a bulk and the boundary contribution. Okay. All of them are local, can be expressed local in terms of local invariants, constructed again from metric and from the gauge fields, if there are any gauge fields. But there is a new structure. Boundary has a normal vector, which will denote as n mu. And in terms of n mu, one can define a new geometrical quantity, which is called extrinsic curvature. Basically, it is a covariant derivative, symmetrized covariant derivative of components of the normal vector. Well, more precisely, maybe I can write it like that. Where H alpha mu is a projector on tangential direction. Extrinsic curvature has dimension 1. And that is why we have more invariants, more possibility to construct new invariants. And even, so both in odd, in even dimensions, and in particular in odd dimension, we can construct conformal invariants defined on the boundary. And that would produce more anomaly terms in the anomaly. H alpha mu. Sorry, here? It's there are two free indices, alpha and mu. It's a normal vector, and alpha is so basically n alpha h alpha mu is 0. From extrinsic curvature, we can construct obviously conformal invariant object, which is traceless part of the extrinsic curvature. So if gamma, usually I want to project this object on the tangential direction, then it will have only tangential indices. And gamma is the induced metric. K is the trace of extrinsic curvature. And this object is transforms nicely under conformal transformations. Plus or minus sigma. Yes. And that is a new, obviously conformal invariant object, which can be used to construct these boundary terms in the conformal anomaly. So basically, obviously, conformal tensors would be the bulk, Y tensor, and this extrinsic curvature. From them, we can construct obvious, by contracting them to each other, we can construct obvious conformal invariants, but there could be some surprising invariants, which are not just simple contractions between them. And plus we have to use Gauss-Kadazzi. Gauss-Kadazzi, these are relations between curvature of defined with respect to induced metric on the boundary and the bulk curvature. How we compute conformal anomaly? everyone has his favorite way to compute. I usually compute conformal anomaly using so-called hit kernel method. So basically, it is a good method if my field is, let's say, free field on the background of the metric. Then my quantum action would be just log of determinant of this operator. I consider here second order operator. If it is the first order operator, like for fermions, I have to square this operator and still use similar expression. And this effective action can be computed using the hit kernel function, which is function of three variables. S is sort of proper fictitious proper time, x and x prime, 2 points on the manifold, and it is e to minus s my operator d. I have to probably project it on some coordinate basis. And then quantum action is just integral given by this integral. So here in the trace, I identify these 2 points, x and x prime. If there are any other indices involved, I have to take trace over that indices and take the integral. What is useful is what is called, okay, here. There are local and non-local, integrated versions of this trace of K. Let me write it in terms of integrated. So it's basically S minus D over 2. D is a dimension of space-time. This is well-known hit kernel expansion. And sorry for reminding you this, you certainly know this stuff. So these coefficients are integrals given by integrals of local expressions, which is a k of x. And in general, d. It has, these coefficients have both boundary and the bulk contributions. And the reason I did all this I reminded this construction only for the only reason that in dimension D, anomaly is given by coefficient AD, coefficient D, when K is equal to D. Plus, suppose we have this kind of action, plus we have to impose boundary conditions. So the boundary conditions have to be conformal invariant. Okay, conformal boundary conditions. If it is a scalar field, there are two possibilities. Usually, we consider projections on two different boundary conditions. So I introduced projector P plus and projector P minus. P plus projects on, P minus projects on Dirichlet boundary condition, which is obviously conformal invariant. And P plus projects on Robin type boundary condition. Well, the form of S depends on what kind of field I'm using. For scalar field, S is just usual thing. K is the trace of extrinsic curvature. Appearance of extrinsic curvature here, all the trace of extrinsic curvature is explained by conformal transformation of the trace. So it's basically changing as d minus 1 normal derivative of the conformal factor. So it is not invariant, but it helps to kill normal derivatives of conformal transformation. For scalar field. For gauge fields, they're more complicated. There are two families of boundary conditions. These are called absolute boundary condition and relative boundary condition. If you're interested, I can put them on the blackboard. Okay. Edge mode as well. That I would like to understand better, answer to this question. How it is related to presence or absence of edge mode. Usually just fixed, these are two conditions which are fixed by conformal invariance. For scalar field, there is no any other boundary conditions. So let me then erase some part of this. So anomaly we start in dimension 3. The integrated anomaly is a combination of so it's clear that there are two ways to have a conformal invariant. It can be either topological. So topological can be Euler number of the bulk or Euler number of the boundary. So they cannot appear at the same time. If dimension is even, then Euler number of the bulk. If dimension is odd, it's even Euler number of the boundary. So in dimension 3, it's a combination of Euler number of the boundary and some conformal invariant one can construct from, as I told you, from a traceless path of extrinsic curvature. So dimension of the boundary is 2. So there can be only traceless path of the curvature, extrinsic curvature squared. That's the only invariant. And C1, C2. Okay, let me write here the spin. So for scalar field, Dirichlet boundary condition C1 minus 1 is plus 1. Robin boundary condition scalar field plus 1, 1. And for fermions, I will explain it a bit later. What is the problem with the fermions? We have to use here Dublin representation, and I will explain why. But at the moment, let me just tell you the values of these charges. It looks like fermions combinations in terms of conformal properties. Fermions are combinations of scalar fields that satisfy Dirichlet and Robin boundary conditions. I'm just saying, yes, in a sense, I will explain it a bit later. Fermions also, a boundary condition for fermions split on 2 parts. So basically on half of components we impose Dirichlet, on the other half Robin boundary condition. Right. If there is a combination of some number of scalar fields, some number of fermions, then we just have to put here certain numbers. How many scalar fields, how many Dirichlet and Robin, and how many fermions. So in D equal 4, there are more possibilities to construct invariants. So D equal 4. We still consider this integrated conformal anomaly. As I said, there is always contribution from the Euler number of the manifold, which now has some boundary contributions, again constructed from bulk curvature and the extrinsic curvature to make the entire combination topological. Plus, of course, in the bulk we have the known y squared term, and on the boundary we have 2 possible ways to construct conformal invariant term. That would be while tensor with 2 components in normal direction and the other 2 components. So for me, this little a and b will be indexes in tangentials. So they are living on the boundary. N is always orthogonal to the boundary. And contracted with traceless path of extrinsic curvature, and plus C, a new term, which is just constructed from the on the traceless part of extrinsic curvature. So A and B are measured on the boundary, in the bulk. They're well known and many times we calculated. So B1 and C are some new boundary conformal charges. And there was a, well, sort of confusion, maybe I would say a problem, that in the way, when it was calculated for free fields, so free fields, just by observation, it was found that B1 is proportional to B for all fields. For scalar fields, any boundary condition, Robin or Dirichlet, fermions, and also gauge fields. I said there are two families. For both families, this relation holds, but for free fields. And we thought that maybe it is there is a reason for that. And the reason was quite clear, because if you, so it means that this invariant doesn't come alone. It comes always as a companion to the bulk invariant. And these two invariants, they come with a coefficient 8. These are precisely what is called Gibbons-Hawking. So this boundary term is Gibbons-Hawking boundary term for Y squared. Basically, if you take a variation of the metric, on the boundary there is a contribution from normal of variation of the metric. If you want to kill it, you have to add these two. And we thought maybe that is sufficiently deep reason. But then Chris came along and said, found models where this is not correct, this is not true. These are models with dynamical theory on the boundary. And these models, B1 is different from 8B. And so these are the theories, as far as I understand, in which field, quantum field lives not only in the bulk, but also on the boundary. And I will always thought that maybe there is a problem with this kind of theories. But I never managed to put my finger on the problem. But let me just explain you what I think. So suppose we have a space-time with a boundary. So let's put this x, z, and y. And boundary is defined at x equals 0. Okay. And my quantum field can propagate through the bulk or can propagate from the boundary. Suppose that I have 2 points on the boundary, and on the boundary I have a causal cone. If it propagates on the bound along through the bulk, it has another causal cone. And I always thought maybe these two cones are not consistent to each other. And it indeed happens in the so-called DGP model. There are different manifestations of this inconsistency. If both bulk and the boundary are flat, just, I don't know, boundary is plane, is a plane, then this problem probably doesn't arise. But even if bulk is flat, but boundary is curved, and signal along the boundary follows geodesics on the boundary, then in general, no reasons to think that these two cones are consistent to each other. That's sort of qualitative ideas that I had, but I never formulated it in. I live on the boundary. You live in the bulk. I send you a signal, you send me back, I received it. Or I can send my signal along the boundary, and it comes faster than your signal. So it definitely creates a problem with causality. Or it may be that signal sent to the bulk is faster than signal sent along the boundary. This is also possible. Ideally, these two cones should be the same. I mean, one should lie inside of another. So d equal 5. D equal 5. Just maybe briefly. I'm not limited in time, right? Why it's not till lunchtime? 10 and lunchtime. That would be logical. Huh? So d equal 5. Okay. Again, it's odd dimensional. That's why topological term is just Euler number of the boundary. And there are 8 different invariants that can be constructed from the wide tensor and extrinsic curvature. So the obvious ones is just various contractions of the extrinsic curvature will itself. So the boundary is 4-dimensional, and we have to construct invariants of dimension 4. The other possibilities are to use wide tensor. So if all indices on the boundary, or one of the indices, or two of the indices, or in the normal direction. So these are 2 indices. Then yes. When one of the indices in the normal direction and 3 others in the tangential, and this is obviously conformal invariant, but it can be using Gauss-Kadazzi relation also rewritten as in terms of extrinsic curvature, some covariant derivatives acting on extrinsic curvature, but these combinations of terms vanish if bulk is flat. Then I have various contractions of wide tensor with extrinsic curvature, A, B, AC, BD, and A n b n. These are k squared contracted with indices a b. These are more or less obvious invariants, but there is one more invariant, which. Sorry. Yes. Yeah. What kind of boundary conditions? You are talking about CFT living on the boundary, or okay. Not only dynamical, but even how, suppose G mu is background field, right? But how correctly define quantum stress energy tensor, this expectation value of T mu, which is supposed to be variation of this quantum effective action with respect to metric. And I want this action to satisfy this so-called Gibbons-Hawking condition. Then when at compute variation, there is no terms which I cannot cancel, right? If there is a variation, so how I should treat this from the point of view of stress energy tensor? But it is partially statical. I mean, I don't really have a strong argument. Okay, and the final conformal invariant term. Conformal invariant term E8, which also I will not write it as quite long, but it has certain normal derivatives of Y tensor, covariant derivatives of extrinsic curvature, and several other terms. But what is important in flat space limit, when bulk is flat, okay, bulk is flat, E8 is not vanishing, and it still can be presented as a certain boundary derivatives of the covariant derivatives of extrinsic curvature, and plus some polynomials in terms of extrinsic curvature. So plus K4 terms. So this eight conformal invariants plus Euler number, we believe that they form the complete basis of conformal invariants which exist in 5D. Okay, let's finish with my first part. If you have any more questions. Let us switch to chiral anomaly and more precisely define boundary conditions for fermions. Cone on the boundary. Okay. It is an interesting problem, but I'm not solving it here. I don't consider this problem here. Of course, it is interesting, yes. Okay, so fermions. Fermions and chiral anomaly. So we start with boundary conditions. We start with boundary conditions. And if there is a boundary, or there is a manifold, space-time manifold, and the boundary, a natural boundary condition would be to make a normal component of the fermion current to vanish on the boundary. That means this should vanish. And this condition is the condition just on the half of components of the fermion. Again, I will introduce two projectors. Basically, they commute to each other. And this condition can be achieved just by imposing Dirichlet boundary condition on the half of components, provided P plus gamma n is equal to gamma n P minus. So basically we substitute here C as a P plus C plus P minus Psi. You substitute it here, and if P plus satisfies this condition, then this condition just reduces to Dirichlet condition on half of the components. But now, when you compute heat kernel, we square Dirac operator, so it becomes second order operator. And this condition is not enough. We need to one more boundary condition to be imposed on the second half of the components. And in order to arrive at these conditions, boundary conditions, let's consider eigen vectors, equation for the eigenvectors of Dirac operator. Then P minus D C on the boundary should vanish. And D, at least in to simplify the story, is just gamma n dn. So it's derivative in the normal direction plus gamma a dA. And so we need a condition P minus D psi dm equal to 0. So P minus becomes P plus when it commutes with gamma n, according to this relation. And P minus acting on this part, we want it to be still P minus, so P minus has to commute with gamma a. So P minus gamma a is the same as gamma a P minus. With all this condition, this is just a normal Neumann boundary condition on the second part of the components. If boundary is curved, these calculations should be modified, and they appear as extrinsic curvature contribution. Okay, let me write it here. So basically, nabla n minus s, p plus psa, dm is 0. This is boundary condition on one half, and Dirichlet boundary condition on the other half of components. And S here is minus k over 2. And these are both conformal invariant boundary conditions. These are both invariant boundary conditions. Sorry? Here they come out naturally.
Previously, I understand because you wanted to prove the conformal anomaly. Here you don't.
No, I assume that my theory is conformal invariant. So my fermionic theory is conformal invariant. Yeah, I want to preserve. But here it's also some kind of comes out naturally. Simply, if boundary is not plane, it's sort of curved, and k is non-vanishing. Commuting p minus will these operators will naturally generate this s, and it is the same s as it is required by conformal invariance. I put here, so it's gamma 0, so it's Minkowski, but that can be done also in Euclidean signature. It doesn't change much. But there is a problem here. Why odd dimensions are special? So basically, we have two conditions on p minus and p plus. This condition and that condition. P plus and p minus projectors. They can be defined in terms of matrix chi. And chi should commute, pardon. Chi should commute with gamma A, anti-commute with gamma n, in order to satisfy these two conditions. And one way to present this, to construct this chi is just this gamma. I will define it gamma star is a chirality matrix, gamma n. So gamma star should anti-commute with all gammas which we have, gamma A and gamma n. This construction works in even dimensions, but this matrix doesn't, chirality matrix doesn't exist in odd dimensions. So I'm not sure how to define properly boundary conditions in odd dimensions. For standard psi spinors. But there is a way out. Way out here is to use so-called Dublin representation for gamma matrices. The simplest way to introduce it is to consider d plus 1 dimensional theory gamma matrices. So this gamma A, where A runs from 0 to D. And then define my D-dimensional gamma matrices as follows. This is just gamma mu. When mu is 0, D minus 1. So Dirac fermions now have twice more components than the standard representation of gamma matrices in D dimension. That is why it's called doubling. And here there are two gamma matrices left. One is gamma D, and the other is gamma 5, which is just product of all gammas. Both of them anti-commute with my little gamma, and both of them can play a role here as a chirality, as a chirality matrix. So basically, I will use gamma D in boundary condition, and with gamma 5, I will define chiral transformation as in a usual way. And then I can compute the anomaly, if there is any anomaly, chiral anomaly in this case. Okay, let me maybe just present the result. Do you have any questions about this? So I will erase this. Is it okay? Okay. Okay, so in D equals 3, I will basically compute so classically this chiral current is conserved, but on quantum level there is an anomaly, and if D equals 3, in this case I use this doubling procedure. There is, and I consider the case when my fermionic field couples to metric and both the gauge field. So there is no gravity contribution, but there is a contribution from the gauge field. This is basically curvature of this field A projected on the tangential on the boundary. So if D equals 4, there is, of course, a contribution in the bulk. Okay, I will skip maybe the numbers. So it's epsilon AA. And there is also a contribution from the gauge field, which are standard. But there is also a contribution from also some number on the boundary. And by the way, it is more or less clear that for chiral anomaly, I get invariants which are also conformal invariant, but odd These are odd conformal invariants. So this is a conformal invariant constructed from extrinsic curvature. Sorry. And there is no boundary term for the due to gauge field. But it appears in 5D. And 5D parity-odd conformal invariants one invariant is just epsilon tensor contracted with, well, while tensor contracted with epsilon tensor on the boundary, it is the same as here, only all indices are living on the boundary, A, B, C, D. But while tensor defined in the bulk, then when one of the components of while tensor is living in the normal subspace, this is also can be rewritten using Gauss-Kadazzi as in terms of extrinsic curvature. Third invariant again while tensor contracted with extrinsic curvature. And finally, there is the contribution from the gauge field to epsilon FF, but on the boundary. So these are all living on the boundary. And we computed the chiral anomaly. So basically, these invariants, there is a prefactor here with pi's D1, J1, D2, G2, D3, G3, and D4. And we have some numbers. D1 is 2, D2 is 3, D3 is 2, and D4 is 48. D4 is 48. So let's complete the story in 5D. Do you have still maybe 15 minutes? Okay.
Tunneling events that change.
Say it again.
They're like a tunneling event, insta-sign, tunneling event that changes the kind of affirm. Do you have any intuition for the term involving extrinsic curvature?
If it will produce any tunneling effect, or it is definitely not topological. I don't see it as topological. No. Which term is topological? Sorry, this? Okay. Okay. I would like to see why it is topological.
Why I would change the chirality.
Not in the moment, but we can discuss it. Any other questions? Excuse me, can you repeat?
So can't I have any terms that mix the, say, extrinsic curvature and constraint?
You mean F and K? It could, in principle, it could, if one construct any conformal odd invariant with F and K, a priori it should appear in the calculation, in the anomaly, but I'm not sure if there is such invariant. Because K is symmetric, F menu naively is antisymmetric. When maybe in high D it will appear, but I'm not sure in 5D. Okay, so now I come to my final subject. This one, no. It's just usual. This is actually Riemannian connection induced, defined with respect to this induced boundary metric. That's why I put here bar. Okay, so there is an interesting relation of all these anomalies with certain things which might be in principle observable. I learned about them only recently, and it is really fascinating. So basically, anomalies can lead to certain physically observable effects, which typically is just appearance of certain currents. Usually, if external magnetic field is applied to the system. Let me just very briefly say about conformal anomaly. I did not say it, but in D equal 4, conformal anomaly also has a contribution from F menu, if there is a coupling of my fields to external gauge field, Maxwell field. And this term, this conformal anomaly will lead to appearance of a current, electric current, which is, I skip all prefactors, vector product of, well, in weak field approximation, so basically Newtonian gravity, which is just vector product of, this is acceleration in gravitational field, so basically acceleration vector product with magnetic field. Did anyone see this before? It's kind of interesting. So maybe I will just flash a short proof of this formula. So this anomaly means that if you have a metric, let's say metric in weak field approximation, Newtonian limit, we can rescale, factorize this 1 minus 2 phi. And that is the conformal transformation. And dependence on phi can be traced from conformal transformation of the quantum action. So it's basically, so this is e to sigma. This is sigma f mu. So to leading order, this is just how conformal action, conformal effective action is transformed. And now electric current. So basically, this is just, sorry, e to minus 2 phi f mu. And conformal, electric current is just a variation of this action with respect to gauge field, which is present here. And it will give me, if skipping all factors, nabla, okay, alpha phi f alpha mu, something like this. And this can be, if mu is space-like index, so alpha is certainly space-like, it will be, it can be rewritten as electric current. I rewrite F in terms of magnetic field. This is just a vector product of gradient of phi and magnetic field. Yeah, technically there is a dependence on phi in G bar also. You want me to write this metric? Or? No, I have in mind the standard. And I factorize this piece. So that's basically H0, G00. And this is quite interesting. Of course, it's, I mean, it cannot be applicable to probably macroscopic systems, but our Earth is a magnetic field. So if we are standing on the equator, acceleration goes this way, magnetic field goes that way, and the electric current goes along the equator. So I'm not saying it should be applicable to Earth, but in certain rotating systems, it could lead to observable effects. And I know this stuff from papers of Maxim Chernodub. But more, okay, this is just, I mean, I find it amazing that such thing happened. Sorry?
You use another gauge field that teaches this current.
You mean, can I remove this by gauge transformation?
Build some sort of exotic theory that we don't consider.
Well, this could be applied to what we call Weil metals, Dirac metals, which can be some quasi-particles can be described by fermions, relativistic fermions, and this would play a role there, so in that particular system. So we need a media made from this conformal matter to observe this effect. I don't know if I answered your question. Well, it can be applied to any theory where there is a conformal anomaly that couples to to Maxwell field, right? That is electric current. This is electric current that couples to my gauge field, which is here. It's sort of quantum electric current. No, it doesn't. Flat, you mean if there is no Newtonian gravity? Yes, it does, yes. Hmm?
Yeah, that's why it sounds
No. I'm not expert in that part, and I can give you maybe more precise not reference, but I made a photo of the names. So Chernodub was Mediano. – 2017. They did not present this result in this way. Instead, they have sort of what they call Nernst type current, which is of this type. It's gradient of temperature vector product with a magnetic field. Simply in these systems, if there is a temperature, gradient of phi is compensated by gradient of temperature, and gradient of phi can be replaced by gradient of temperature. Yes, I can. Right. There is also Vf, which is Fermi velocity in this formula. Sorry, I cannot find this. Okay, some more coefficients here. This is what we have. Yeah, E squared is a beta function. Okay. Is similar in the spirit. Effect can be defined for derived from chiral anomaly. So the corresponding quantum action which generates the chiral anomaly can be easily constructed if we introduce chiral gauge field. So we make this chiral transformation local and introduce the corresponding gauge field to kill gradients of chiral transformation. Then the quantum action could be written in terms of the background field. So this is the background field plus Maxwell field. And just skipping all factors, I'm talking about D equal 4 chiral anomaly which arises in the bulk. Square root of G, A mu 5, vector S mu. A vector S mu is such that its divergence is precisely epsilon mu alpha mu alpha beta F mu F alpha beta. So S mu is 2 epsilon mu alpha beta nu A alpha F beta nu. So chiral current would be just variation of the action with respect to chiral field, chiral gauge field. And that would be S mu. And then you, taking the divergence, we get the usual form for the chiral anomaly. So now we have an action where there is a background field, chiral field, gamma A5, and also my Maxwell field. So variation of this action with respect to A mu, which is the Maxwell field, will give me the current, electric current, electric 4 current. Electric 4 current. So basically, I define J mu as a variation of my action with respect to gamma 5, A mu. And it has several components. There is the prefactor, which depends on the chiral, this coefficient in the chiral anomaly, epsilon mu nu alpha beta, A nu 5, F alpha beta. And in this science, people usually assume that gamma 5, A5 has only one non-vanishing component, 0, which is identified with the chiral chemical potential. So it is a constant. Its derivatives 0. And that means that this current has only space-like components non-vanishing, and that is basically this current proportional to magnetic field. Okay, this kappa would be sigma F mu 5, 8 pi squared, where sigma 5 is the chiral value of this coefficient in the chiral anomaly. And this is, of course, well known by now, chiral magnetic effect. It is interesting maybe to mention that same game can be played for the gravitational anomaly. So there is a contribution in the to chiral anomaly. Well, first it comes from the gauge field, and the other piece comes from gravitational field. And the second term also can lead to certain observable in principle effects. So basically, considering Newtonian approximation, so S is traceless. It presents all this gravitational atom leads to appearance of stress energy tensor, in particular to 0I component of the stress energy tensor. That basically sort of pointing vector which describes flow of energy. There is a coefficient here, epsilon k L I dl delta 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 W WK. And this looks pretty much as a magnetic field. And indeed, defined for this vector WK. And this is indeed the case due to gravito-electromagnetic analogy. So this component, basically, which describes rotation of the system, can be associated, well, with gravitational sort of electromagnetic field, and its curl, basically KLI dlWK, is corresponding gravitational magnetic field. So this is basically delta is a Laplace operator in space, like in space in three-dimensional space. B I. So it again is similar, quite similar to that. If we define the current here, this could be, it's not anymore electric current, but energy flux. I don't know how to define, maybe P. I. And this brings a similar, makes a similar effect for the gravitational part of the anomaly. Let me just finally use 2 minutes, because my talk is about the boundaries. In 2+1 dimensions, we have the chiral anomaly, basically and I use this anomaly formula in a particular case when my 2+1 dimensional fermions are living on the plane z equals 0 plane. So they are basically living in 2 dimensions. But the gauge field is four-dimensional. It couples to the system. It comes from 4 dimensions. And my system lives here. And these are four-dimensional fermions. They have 4 components. And they couple to background, I don't know, four-dimensional gauge field. And then in a similar spirit, I can define, I deduce the electric current, which lives on the boundary. Again, skipping some prefactors. It's epsilon AB A5B. Again, I introduced this gauge chiral field. And again, I assume that only 0 component to the chiral gauge field is non-vanishing, and it is associated with the chemical potential. And then this tells me that there is a current along the boundary. So basically, if I introduce here a tangential vector, then it will be some coefficient mu5 t. So there is a current going around along the boundary of this 2+1 dimensional system. Okay, that's all I wanted to tell you. Thank you.